So let us start. Last class we found how to balance when different masses are rotating in the same plane. Now there is another situation in which different masses are rotating in different planes or several planes. They may be parallel planes. So here it is shown there are four masses 1, 2, 3, 4. They are rotating in different planes and they need to be balanced by placing masses at say M and L. So these represent different planes 1, 2, 3, 4 and M and L where you need to place the balancing masses. So you may think that so why do we require two balancing masses? Of course we can do away with single balancing mass, but normally practically it would be convenient if you place two balancing masses when you take into account the practical situation. Now, even if there are no balancing masses, the system can be balanced by itself. See, 1, 2, 3, 4 by proper arrangement, we can have perfect balancing, but they may bring practical inconvenience. Even with three masses alone, we can have perfect balancing. But if only two masses are there, we can never have perfect balance. But if you have 1, 2, and 3 masses, by the system itself, it can be balanced without placing in additional masses at any additional planes. But here, let us see the general picture. So when you have four masses, we need to balance using two masses placed at two different situations. So in this kind of situations, if you want to achieve perfect balancing, you would need to have sigma f is equal to 0, sigma c couple is equal to 0, sigma f is equal to 0, sigma c is equal to 0. First of all, we can easily draw the force polygon. It should be closed. It is to be balanced. So force polygon, as you see, this is the end view, side view. Okay, so from this we can easily draw the angular orientation and complete the force polygon. For example, force polygon first masses. This vector can be drawn like this. M1 first force, say F1. Then M2, this is a direction, say F2. Then M3, this is a direction, F3. And M4, this is a direction, F4. Now M. Suppose you assume that this orientation is known and this mass is known. So this is a direction. This is the direction because it's radially ordered centrifugal force. And ML is in this direction. So this. So it should be closed. So this we can indicate by dotted because these are balancing masses. So this is Fm and this is Fl. So if it is closed, we can easily find out. Now normally in problems, one will be unknown and finally this suppose Fm may be known and Fl may be unknown, and you can easily find out the value of Fl, and from that you can Fl, you know, Mr omega square is common, M into R you can easily find it out. We have completed force polygon. Now let us draw the coupled polygon because in this case the coupled polygon also should be closed. So how to draw the coupled polygon? So here you can see that this NTU, look at this NTU. This M1 is appearing like this. So that means the mass is going like this, the force is going like this. That is why its NTU is coming like this. And we are taking moment about L because this is one L and M are the balancing masses. So its value should be found out. So by suitably taking reference plane as L, we can avoid one unknown. So it would be better to take reference plane at the balancing mass. Otherwise, you may not be able to complete the polygon. So, but if you take strictly speaking, when you take moment about any plane, it should be balanced. So this is the direction of force and this is the length vector because for first mass this is the length vector or the radius vector. So this is force and this is the radius vector. So this is R, this is F. So R cross F will be the coupled polygon. So the coupled diagram, it will be C1 will be like this. And C2, the second force, if you find it out, you can see that it will be something like this. See, and C3, it will be something like this. And C4, it will be something like this. C4 and M. You want to get that something like this. C1 is like this. C2 should be anti-clockwise. C2 like this, and C3 should be like this. C3 should be like this. C3 should be like this. C4. C4 is like this. C4 is like this. CM is like this. And this is C2 because so this will be the coupled word. Now now you can see that if you rotate C1 by counterclockwise or the entire diagram by 90 degree in the counterclockwise direction, what you are going to get is this is C1 and this is C2 and this is C3 and this is CM and this is C4. That means you are getting the force vector polygon. See, if you rotate the actual coupled polygon diagram by 90 degree in the counterclockwise direction, you are getting the coupled polygon whose direction is equal to that force polygon. So the advantage that is we can easily correlate with the force polygon because we are interested in the relative angular orientation, because the absolute value of this C1 C2 this polygon, coupled polygon, or the position of C1 C2 C3 4 doesn't matter. We are interested only in the relative angular difference between C1 C2 C3 C4. First class I did tell you. If we horizontal line assume the entire thing 10 degree rotate balancing this polygon 90 degree rotate coupled polygon complete absolute value doesn't matter, but that will bring convenience. Now we can easily complete the coupled polygon because C1 actually the force direction F1 is in this direction. Okay, but you may think that C1 is coming like this. It should have come, but why? Because we have defined the reference at this point. So what happens? This couples to the left, so the radius vector to the left will be taken as positive if we take it as negative, and to the right the radius vector is positive. So the sense will differ. So as far as this value is concerned, this C1 will be against the force polygon. Not against the force polygon, against the force. So this we can easily mark the coupled polygon because this value will be negative in the opposite of force. Now C2 is same as direction of F2. So this is C2 and this is F3 and this is F4 and this is F1. Sorry, this is C3, this is C4 and this is CM, and finally one of the value will be unknown. So this value, this will be CL. Sorry, CL will not come. because one value will be 0. When you take moment over this one will be 0. So finally your Cm should be like this value Cm. So in this way coupled polygon can be easily drawn. To make you understand this one, how to help you to draw this coupled polygon and force polygon easily, you can easily draw a tabular form. So which I will explain. So first thing you can serial number where you can mark reference plane 1, L, 2, 3, M and 4. Then mass, radius, then force by omega square, distance from reference plane, then coupled by omega square, because this let it be M1, this is MM, this is M2, this is M3, MM and this is M4, and this is R1, RM, R2, R3, Rm, R4. So F by omega square, centrifugal force by omega square is M1 R1, M Rm, M2 R2, M3 R3, MM Rm and M4 R4. Distance from reference plane, say L1, it should be negative because it is measured in the left direction, and the other one, since this is reference plane, this is L, M and R. So this is 0 because 0 distance. This is M2 R2, L2, M3 R3, L3, MM RM, LM, M4, R4, L4. So here you can see that, this value is that this will be given and this is 0, and perhaps this will be the unknown quantity because this is where at this place we should place a balance mass. These are known quantities 1, 2 and 3, and 0 is a known quantity. This value also is a known quantity. So here you can this is distance. So this you can mark it as L2, L3, Lm and L4. So coupled by omega square, that is M1 R1 minus M1 R1 into L1, here 0, M2 R2 L2, M3 R3 L3, and here MM RM Lm, and here M4 R4 L4. So here you can see that if you look at the force column, this will be unknown, this will be unknown. So two unknown, and you will not be able to complete the polygon because but here if you look at this column, this will be given, this is known, this is known, this is known, this is known, this is unknown. So note that balancing should be achieved. This polygon should be completed, closed. So we can easily start drawing it. Say C1, this one like this direction because minus sign. The other one this direction, this direction, and finally the closing vector should come like this. So this will be the unknown value, and it will give the magnitude of the vector and the direction. So this is known, this is known, this is known, this is known, and the fixed vector will be unknown. So having got this one will be known. So this one will be known. So if you look at the first column, there will be only one unknown out of 6. So the sixth vector will give the unknown value of this. So that then also we can solve it. That we will understand by doing a problem.